We're jumping right into a really fascinating explainer today. We're going to track the exact life cycle of a message as it travels between an application and a large language model. But, we aren't just looking at any normal, everyday message path. We're tracking exactly how Headroom intercepts and processes data payloads to massively shrink costs and manage those pesky token limits, all without losing a single ounce of performance or accuracy. It's a brilliant approach to a problem we all face, and we're going to uncover exactly how it works under the hood.
Okay, let's look at our roadmap for today. First up, intercepting the request. Second, the transform pipeline. Third, provider cache optimization. Fourth, smart retrieval and learning. And finally, number 5, what Headroom leaves alone. Let's dive in.
Section 1. Intercepting the request. The entry points.
So think of this as the starting line. It's the exact moment a message leaves your application and first knocks on Headroom's door. Headroom is incredibly flexible with how it catches that message, intercepting the request right between your app and the LLM provider. It basically does this through 3 main entry points. First, there's SDK mode, where you simply wrap your LLM client with a Headroom client. Super easy, minimal code changes. Then, you've got integrations, which give you framework-specific setups for things like LangChain or Vercel AI SDK. But honestly, the absolute standout here is proxy mode. If you run the Headroom proxy and point your client at it, you literally have 0 code changes beyond updating a base URL. It just seamlessly slots right into your existing infrastructure.
Section 2. The transform pipeline, the core engine. Now we're stepping onto the factory floor. This is where the actual optimization magic happens. Every single intercepted message flows through a sequence of 3 independent transforms: the cache aligner, the smart crusher, and the context manager. And what's really fascinating about this sequence is just how resilient it is. Because these stages are totally independent, they're safe to skip, and more importantly, they fail gracefully. If anything goes wrong in a stage, Headroom just returns the original content completely unchanged. So there are no broken apps, just a really safe progression to shrink costs and manage those strict token limits. Let's break down stage 1, the cache aligner. This is a brilliant solution to a very, very frustrating problem. LLM providers like Anthropic and OpenAI have caching systems, right? But if you have jittery, dynamic data right at the top of your system prompt, say a constantly changing date, a new UUID, or a session token, it immediately breaks the cache. The cache aligner's secret sauce is that it extracts that dynamic content and moves it all the way to the end of the prompt. By doing this, it completely stabilizes the prefix, allowing those provider caches to finally hit consistently on repeated calls.
And honestly, here's the best part. Doing all of that dynamic extraction and realignment, it takes sub-millisecond time. We're talking virtually 0 latency overhead introduced to your app. You get perfectly aligned caches without slowing down your user experience by even a fraction of a heartbeat.
Once aligned, the message enters stage 2, the smart crusher. Think of this kind of like a hyper-organized Marie Kondo for your data. It doesn't just blindly throw things away. Instead, it analyzes tool output content and runs complex statistical analysis, specifically using the needle algorithm on bigram coverage to selectively compress the data. So it intelligently trims the fat, but completely preserves the crucial meat. Errors, anomalies, and distribution boundaries, those are kept unconditionally. If a tool output fails or acts weird, trust me, the LLM will definitely see it.
Now, what's really striking here is just how massive the token savings are across different types of content when that smart crusher goes to work. JSON arrays of dictionaries are compressed by 83 to 95%. Build and test logs shrink by up to 94% using pattern clustering. And HTML content, which we all know is notorious for eating up tokens with useless tags, gets reduced by around 95% using article extraction strategies. It just factors out all the constant fields and hands the LLM the pure, concentrated signal it actually needs. To understand how it achieves this without breaking your app's logic, we have to look at the internal retention split. When Headroom decides what to keep, it guarantees 30% from the start of the array, just to ensure schema hints are preserved perfectly. Then, it keeps 15% from the end to ensure the most recent data is there. The remaining 55% is determined by an importance score. It's basically a perfectly balanced diet for your LLM, prioritizing the most important items while always safeguarding structure and recency.
Finally, the message hits stage 3, the context manager. This is your ultimate gatekeeper, ensuring your message will absolutely never break the model's context window limits. It has 2 modes. The default is a rolling window, which simply drops the oldest messages first while making sure to preserve the system prompt. But the advanced mode is intelligent context. This actually scores every single message on 6 distinct dimensions, including semantic similarity, token density, and error indicators, before it drops anything at all. It ensures that if something has to go to fit the window, it's strictly the least mathematically valuable piece of the conversation.
Section 3. Provider Cache Optimization. Okay, here is where stage 1 really pays off. After the pipeline, Headroom applies provider-specific cache hints to that perfectly stable prefix it created earlier, and the resulting token savings on cached content are just huge. We're talking up to 90% savings with Anthropic's cache control, up to 75% utilizing Google's cached content API, and up to 50% with OpenAI's automatic prefix caching. This is exactly where the structural optimization translates directly into massive cost reductions.
Section 4. Smart Retrieval and Learning. Now, you might actually be screaming a question at me right now. What happens if the LLM actually needed the exact data that the Smart Crusher or Context Manager just dropped? Well, that leads us directly to Headroom's advanced safety nets. The absolutely crucial point here is that Headroom's compression is completely reversible. It uses CCR, or Compress, Cache, Retrieve. Whenever data is compressed or dropped, the original full-fat content is stored safely in a local compression cache. If the LLM is analyzing the compressed summary and suddenly realizes it needs those original fine-grained details, it can simply request a retrieval using a specific CCR_retrieve tool call. This gives developers ultimate peace of mind. Nothing is ever permanently lost. It's just neatly filed away until it's explicitly needed. Furthermore, Headroom is actually getting smarter with every single call, thanks to Tween, the tool output intelligence network. It doesn't just rely on cold start heuristics forever. As a tool is used repeatedly across your sessions, Tween builds up a highly detailed statistical profile. It learns exactly which fields matter to your specific LLM, which items actually get retrieved from the CCR cache, and what compression strategies are most effective. It learns your specific tool behaviors over time and feeds that intelligence right back into the Smart Crusher.
Section 5. What Headroom leaves alone.
Let's bring it all home. For an architecture designed entirely to intercept and transform data, its core principle is actually safety and protection. There are very strict boundaries here. User messages? They're never compressed because raw user intent must be preserved perfectly. Raw code? It passes through entirely unchanged unless you explicitly enable AST compression. Model responses? They're returned to your app exactly as the provider sent them. And short content, like cool outputs under 200 tokens, just passes right through because compressing them wouldn't justify the sub-millisecond overhead. Headroom knows exactly when to optimize and exactly when to just get out of the way. We've seen how Headroom intercepts, dynamically crushes payloads, aligns caches, and guarantees safety through reversible retrieval. So I really want to leave you with a thought to challenge your current architecture constraints. If your LLM integration could automatically compress noise by up to 95% without ever losing critical errors or user intent, how much more complex and powerful could your tool outputs become? By removing the fear of context windows and soaring token costs, Headroom doesn't just save you money, it fundamentally changes what you can build. Thanks for joining me on this explainer, and I highly encourage you to see how this architecture fits into your own stack.